Let us discuss about electrical properties of solids. On the basis of their conductivities, solids can be classified into three types, namely conductors, insulators, and semiconductors. Conductors can be classified into two types, namely metallic conductors and electrolytic conductors. In metallic conductors, flow of electricity is due to the movement of electrons. Hence, the substance will not get decomposed. Whereas in the case of electrolytic conductors, flow of electricity is due to the movement of ions. Hence, the substance will get decomposed. The next important difference is that in metallic conductors, conductance will decrease with increase of temperature. This is because with increase of temperature, kernels will start vibrating. Kernels are positively charged ions of metals in crystal lattice. If these kernels vibrate, electrons cannot travel faster. Hence, the conductivity decreases. Whereas in the case of electrolytic conductors, conductance will increase with increase of temperature. This is because with increase of temperature, force of attraction which is holding the ions will get weakened. Hence, the ions can move freely, which will increase their conductance. Before discussing about band theory, let us discuss what are bands, valence bands and conduction bands. Atomic orbitals or molecular orbitals which are so close in energy will merge into a band. Look at the figure 1. Sigma 2s orbitals of n number of lithium atoms are having similar energy levels, or they are having very close energy level. So they are seen as a band. Similarly, anti-bonding sigma star 2s orbitals of lithium also has close energy levels. So they are also seen as a band. Let's see what are valence bands. The band occupied by valence electrons or highest occupied band, that is occupied band that is having maximum energy, will be called as valence band. Next we have conduction band. A partially filled band or lowest unoccupied band, that is unoccupied band which is having minimum energy, is called conduction band. The electronic configuration of magnesium is 1s2, 2s2, 2p6, 3s2, 3p0, 4s0. In the case of magnesium, valence electrons are present in 3s2 energy level. So that band is called as valence band. And the lowest unoccupied band is 3p0. So that band we call it as conduction band. In the case of lithium, valence electrons are present in sigma 2s bonding molecular orbital. This molecular orbital we call it as valence band, and the unoccupied band which is having minimum energy will be anti-bonding sigma star 2s molecular orbital. So that orbital we call it as conduction band. This is shown in the figure 1. Based on band theory, we can explain why conductors have very high conductivity. This is because in the case of conductors, valence band will be partially filled, or the valence band will overlap with the conduction band. Hence, electrons can flow easily under an applied electric field. Hence, the metals will show high conductivity. The solids which are having conductivity range of 10 to power of 7 ohm inverse meter inverse will be classified as good conductors. In semiconductors, the gap between the valence band and conduction band is small. Therefore, some electrons may jump to conduction band and show some conductivity. So semiconductors has conductivity between conductors and insulators. In insulators, the gap between the filled valence band and the conduction band is large. So the electrons cannot flow readily. Hence they have very small conductivity. Semiconductors are classified into two types, namely intrinsic semiconductors and extrinsic semiconductors. Extrinsic semiconductors are further classified into two types, namely N-type semiconductors and P-type semiconductors. Now let us discuss about intrinsic semiconductors. The pure form of group 14 elements, that is silicon and germanium, will be called as intrinsic semiconductors. The conductivity of these intrinsic semiconductors will increase with increase in temperature. Let's see how it is so. Let's take a silicon atom. We know a silicon atom has 4 valence electrons. So it is tetravalent in nature. So each silicon atom can form 4 covalent bonds with 4 neighboring silicon atoms. So if you take a silicon crystal lattice at 0 Kelvin, it will not have any free electrons. So it will behave as a insulator. It will have very low conductivity. But when I am going to increase the temperature above 0 Kelvin, the covalent bonds which are holding the silicon atoms together can break. Hence, the electrons will be released. These electrons are free to move. Hence, they will show some conductivity. So, the conductivity of silicon atoms above 0 Kelvin will be more. This is shown in the figure 2. To an intrinsic semiconductor, when we add appropriate impurities, intrinsic semiconductor will be converted to an extrinsic semiconductor. Now let's see what is doping. Doping is the process of adding appropriate impurities to intrinsic semiconductors to increase their conductivity. Impurities can be electron-rich impurities, that is group 15 elements, or electron deficient impurities, that is group 13 elements. Now let's understand the term dopant. The impurity added to a semiconductor will be called as dopant. For example, to silicon, if you are going to add phosphorus as impurity, phosphorus will be called as dopant. In the tabular column, we have the difference between intrinsic and extrinsic semiconductors. When a intrinsic semiconductor, that is pure form of silicon or germanium, is doped with pentavalent impurity, that is group 15 elements, phosphorus or arsenic, a N-type semiconductor is formed. Let's see how the N-type semiconductor is formed and which is responsible for its conductivity. Let's take the silicon crystal lattice. In that we are going to add small amount of phosphorus as impurity. We know silicon is a tetravalent atom, whereas phosphorus is a pentavalent atom. That is, phosphorus will have 5 valence electrons. So, phosphorus atom will use its 4 valence electrons out of 5 to form 4 covalent bonds with the neighboring 4 silicon atoms, and it will have one free electron. This fifth free electron will be free and it can move. This delocalized negatively charged electron will be responsible for the conductivity of this type of semiconductor. Since the negatively charged electron is responsible for the conductivity, This type of semiconductor will be called as N-type semiconductor. Now let's discuss about P-type semiconductor. When an intrinsic semiconductor, that is pure form of silicon or germanium, is doped with trivalent impurity, that is group 13 elements, boron, aluminum or gallium, a p-type semiconductor will be formed. We know silicon atom is a tetravalent atom. It has 4 valence electrons, whereas aluminum is a trivalent atom. It has only 3 valence electrons. So when you are going to add small amount of aluminum to silicon atoms, aluminum will form 3 covalent bonds with 3 neighboring silicon atoms. With the fourth neighboring silicon atom, it cannot form a complete covalent bond since it is not having fourth electron. The place where the fourth valence electron is missing in aluminum is called a electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole. In the figure you can see an electron from adjacent silicon atom has occupied the hole created by the electron deficient impurity, that is boron atom. As a result, the hole is shifted from boron to that adjacent silicon atom. So, if this is going to continue, it will appear as if the hole is moving from one place to another. We know in the presence of electric field, electrons will move towards the negatively charged plate. For the movement of electrons, it will use these holes. So, holes will appear as if they are positively charged and they are moving towards the negatively charged plates. This is because when electrons are moving towards positively charged plate, the holes will be moving in the opposite direction, that is negatively charged plates. So holes, they will not have any charge, but they will appear as if they are having positive charge and they are moving towards negatively charged plate. So in the case of p-type semiconductors, holes are the charge carriers and they are assumed to have positive charge. Hence these semiconductors are termed as p-type semiconductors. These are the applications of N-type and P-type semiconductors.